Hi, I'm Ali Syed, Master of Science in Mechanical Engineering. Here we are going to discuss a brief description about fatigue and damage tolerance analysis, which is nothing but F&DT analysis. To understand this part of analysis, we need to understand what exactly is a fatigue. Fatigue is nothing but a crack on the material of the component which you will get because of the cyclic loading and unloading of a constant load or improper load. For example, as we see, there is a chance of having a crack on the material, on the component, even if the load is much lesser than its yield point. It's because of the cyclic loading and unloading of the constant amount of the load on the component. So that thing is actually a fatigue. So you can see actually the fatigue in the parts of the stages. Once you get the small crack, it is called a fatigue. So even after that, if the loads are applying constantly on the component, so there is a chance of the crack to increase its length, which is nothing but a crack propagation. As here you can see the crack is increasing. So even after that, even if the load is being applied, so that crack will lead to a fracture, which will be the failure of the component. So this fatigue is nothing but this fatigue mechanics. Like actually what exactly we do in the fatigue is we study how is the crack is being, how we are getting the crack on the component, and what are the major things which are causing for that crack on the component. We'll see that how they are getting generated in the further. So main thing, once we know about the fatigue, we need to study about the fatigue life. This is a very important thing for any component. So any manufacturer, when they manufacture a component, they need to study what is the life of that component. So for example, if there is any component, the life of that component will be 6 months or 8 months or 10 months. The manufacturer say you need to replace this component for every 6 months. Or for example, they will say in automobiles you need to replace this component after 1000 kilometers or 2000 kilometers. That is the life of the component. So that once they mention the time, the component will reach to its fatigue life. That is the peak point. So if after that there are chances of having a crack and the failure of the component. So that thing is really important for a manufacturer to study for each and every component. So actually for the standard materials like aluminium, iron, for most of the materials there is a standard SN curve, which is nothing but a stress towards the number of cycles. Using this curve you can see at what stress, at how many number of cycles that material or that component will be risk free, will not get any cracks, will not go into the fatigue stage. So this SN curve is actually calculated in the free state. So once all the values what you get over here is a free state. So once you get the component, you need to do the few testings on it. You need to do it for the 1000 cycles or 2000 cycles at high cycles or low cycle frequencies, and then you need to test the component, and then you can find out where exactly you are getting the cracks. We'll see what is the actual factors which will affect on the fatigue life. Like for example, if there is a component and the fatigue life of that component is for example 1 year, but sometimes what happens is actually the component will fail at the end of 8 months or 9 months. What exactly the factors which will affect the fatigue life? Firstly is a cyclic stress test. It is nothing but a cyclic loading or unloading of the loads exactly on the same position of the component. Initially, each fatigue starts with a microscopic crack, which is not visible to an eye actually. So as go on, there is a load applying on the component. That crack will increase its length, and eventually it will run to the fracture. So the point is, the main factor which actually causes the fracture is the cyclic loading, which is not the cyclic stress state. So we need to study what is the stress being applied on the component, and you need to see if there is anything you can do to reduce that size, to reduce that strength. Sorry. So that the actual fracture limit to be, we can reduce the fatigue life actually. So first point, we need to look for the stress state, and the second is the geometry. Geometry also plays a crucial role in this fatigue. For example, we can say if there is a bar and if you give the support over here, and then if you apply the constant load over at the end of the bar, there is a chances of having a fracture or a crack at any point of this load. In the design compatibility, if you just give the support at the end of the bar, inclined anyway, so even if you apply at the end, the load, then the fatigue life increases. Definitely there will be a crack in between somewhere over here, but the fatigue life will be much higher because the design of the geometry of this component is totally different to the earlier one. So even the geometry also plays a crucial role over here. Like for a complicated component, you will have the weak links, or you will have a complex geometry or complex connections of the surfaces, which will also lead into crack. And the other one is a material type. Like for example, like material has its own strength. So if the stress value or its strength concentration goes beyond that point, there are chances of getting a crack. So material also plays a crucial role. And the residual stress. Residual stress is nothing but while manufacturing the component, like for a casting process or any process, like there is a chance of having a air bubbles or porosity in the component because of the manufacturing process. Even that will reduce the fatigue life. And also the surface quality. If the surface of the component is rough, there is a if the surface quality of the component is rough, then you will have a microscopic cracks which will be on the surface of the component, which will increase its length, which go on stress concentrations on it. So these are the main factors which will actually cause which will affect the fatigue life of a component. So how we need to study this process? So once you get this crack stage, what are the things which are actually taking? Like what are the things which are actually going to the next stage of crack propagation, where the crack is being increased? So we'll study what exactly the data we need to study for that. The first thing what we need is applied load. We need to calculate what is the load being applied on the component, and then we need to calculate the residual stresses, like stresses ending because of the design complexity of the component, and we need to have the size and the shape of the part, exact dimensions, and also you need to have the size, shape, and the location and the orientation of the crack. For example, if you see a small crack over here, you need to have its location, you need to have what is the size and the length of the crack, so that you can study in what way the crack is moving because of the load or because of the stresses which are in the component. So if you have these things, you can study in how to stop that crack, or else you can say stop the cracking. So that things can be easy to study in this process. That mechanics is known as the fracture mechanics, studying about the whole cracking. There are many ways you can stop the cracking actually, by changing the design, or by reducing the stresses, or by reducing the residual stresses by a very good manufacturing process. This everything can be done. But the main thing what actually they do over here is design against the fatigue. There are three principles in that. Important principles of which actually the design against the fatigue is taken. Where the first one is stress below the threshold fatigue limit. First you need to see if the stress limit for a component, if the stress limit of a component is point A, then you have to try to reduce the stress which is being applied on the component should be less than A. For example, less than 20. So you have to see if you can reduce that strength, by which you can definitely increase the fatigue life. And the second is design for fixed life. If there is nothing you can do, like if you cannot decrease the length or the stresses being applied on the component, then you have to see if you can maintain that component without failing for fixed life. If that can be done, and then you can design for the fixed life. Like for example, earlier as I mentioned, you can fix the component by saying that you have to change for 6 months. If the manufacturing is saying that you have to change it for the 6 months, it means the component will never fail in that 6 months. So that way you can design for the fixed life, and then or else you can replace the part. If there is anything you cannot do even in the design, if the design is very complex and there is nothing you can change in that, and you have to go along with that for the process, then you have to keep an eye on the part for every 3 months or for the time which actually mentioned by the manufacturer, to see if there is any cracks or to see if there is any failures in the component, so that you can replace it. So these are the main actually design against the fatigue principles which is done. So far what we have done is a fatigue tolerance. Like fatigue tolerance is nothing but study the fracture mechanics, where you can study how to increase the fatigue life, how to stop the cracking and everything. So even if you got the crack, even if the component got failed, okay, the component should sustain its defect until that component is being repaired. That is known as damage tolerance. Damage tolerance is nothing but ability to sustain the defects until it gets repaired. For example, if you got a small vehicle or anything, for example, you see like the tire gets punctured. That is nothing but failure of the tire because of the hole on the tube and everything. But still, you will manage that to take till you get it punctured. You get the air filled. So there will be a damage tolerance which will be calculated so that your tire or your tube, anything can sustain its level. You cannot drag in the punctured way your vehicle to 10 kilometers or 12 kilometers. That will be out of the way of the tolerance, which will affect the tube. So these are the few things which, for example, these are the simple things which will actually damage tolerance come into the consideration. But this thing is mainly used in the aircrafts. For example, like as this damage tolerance is mainly used in the wings of the aircraft, where the whole structure in the wings is damage tolerance. So that if there is anything at the failure at the one point which can be controlled by the other supports, so that thing will come into consideration, the damage tolerance. And now we see what is the damage tolerance analysis. Damage tolerance analysis is nothing but a list of schedule where you need to study each and every area of the component to see if there are any damage or if there are any processes which will fail this component. First thing is assume initial damage. Anything unless and until we test, or unless and until we put it in the machine, or unless and until we put it in the assembly and we run it in the reality, the whole dynamic analysis, dynamic loads will apply on the component. Only then, even that too for a year or 2 years, only then we can see what is the actual problems a component can face. But as we already know what actually the process, to some point we can assume what will be the initial damage, where the initial crack will start. So we need to study the whole component and the process, and we need to see where is the initial damage, so that we can study on it and we can rectify on it. And the second one is stress that will cause the crack and the geometry, that will cause the crack. It's nothing but the increasing the stress going beyond the end point, or the stress going beyond its fatigue limit. If it is going beyond that, there is a chance of having crack. So we need to study that as well, like stress that will cause the crack and the geometry. Ability of the material. We need to see if the material can withstand the load which is being applied. Is that within the limits of the end point? We need to check all these things of the material as well. And also, to study the damage tolerance, you need to study what is the largest crack on the part. Few components will have 3 cracks or 4 cracks because of its weakness. You need to see the point which is you are having a large crack, you will have the fracture at that point first. So we need to study what exactly is going on at that largest crack. So that thing you need to study for the damage tolerant analysis. And the second is the duration, life of a part. Here you need to see a manufacturer release a component. So from the manufacturer to the fracture, what is the duration? So we need to see how long it took for a component to fail, how long it took for a component to get the crack and then to get the fail from the manufacturer. So this will help to study on this component or the damage tolerance analysis as well. And then assumption of failure in adjacent components. This is a very important thing actually, because the failure of one component should not affect the adjacent components. If the failure of the one component is failed, the adjacent components which are having, that should not take overload which may cause the failure of that components. So that should be at least something, the adjacent components should be checked in such a way so that failure of this component will not be there. So even if the failure of this component is there, the other components should adjust the process and should not fail by himself. So that thing is also something which you can do in the which you will do in the damage tolerance analysis. So this is a very important analysis in these days. This thing has come into consideration in today's it's very much because the failure of engineering anything is taken as a very shocking in these days in the world. So that is the only reason where the research is going really in depth, because the safety measure is a very important thing. So fatigue and damage tolerance is nothing but even at the breakage, even at the failure, the component should run to some extent until it gets repaired, until it gets to the safe position. So that thing is really important. That is the whole scenario, at the end scenario of this whole process. So this is the overview of the fatigue and the damage tolerance. Thank you.